Welcome to the deep dive. You click an app and magic happens.
Right.
Groceries show up, you slay some dragons, connect with friends halfway across the world.
Yeah, it feels effortless.
But behind that slick digital surface, well, there's this whole structured world, a really fascinating blend of art and science, turning these complex ideas into something that actually works.
It really is. It's so much more than just, hammering out code. It's a systematic approach, disciplined, really focused on building reliable, effective tools that solve actual problems.
And that's exactly what we're getting into today. Our mission really is to unpack the core ideas behind software engineering principles. We've gathered a whole stack of sources that give a pretty comprehensive look at how software gets made.
From the kind of old school traditional methods.
Right, all the way through to modern agile ways of working, how you figure out what actually needs building in the first place, and even how you visualize these, often really complex designs.
Think of this as your shortcut, maybe, to understanding the landscape of software development.
Exactly. So let's dive in. When you start peeling back the layers of pretty much any software project, you usually find this thing called the software development lifecycle, or SDLC.
Right, the SDLC.
Yeah, think of it like the basic playbook, a series of phases that, well, almost all software goes through in one way or another.
It really is. It's a structure, a path designed to bring some order to what could easily be chaos. It typically kicks off with planning.
Okay.
Which is essentially figuring out what an organization actually needs from its information systems and, how to prioritize all those different needs.
Makes sense.
From there, you move into analysis. This is where you really dig deep, study the requirements, structure them. What problems are we actually trying to solve here?
Right. And once you've got a handle on the what, then comes design. This is translating those maybe abstract requirements into concrete specs, the architecture, the UI, the database. Like a blueprint.
Exactly, a blueprint. And only then, with that solid plan, do you get to the actual development, the coding part.
But it's not done then, is it?
No, definitely not. Next up is integration and testing, making sure all the bits and pieces work together, that the whole system does what it's supposed to do.
Yeah.
Then comes implementation, getting the system actually installed, rolled out, supported within the organization.
And finally,
maintenance. Because software is almost never set it and forget it. There are always bugs, updates, improvements needed down the line.
So the strengths seem pretty clear. Control, having detailed steps, it's probably easier to maintain, especially for big, predictable projects.
Yeah, that control aspect is a big one.
But what's interesting, and our sources really point this out, is that its main weakness often comes from that same structure, its rigidity.
Couldn't agree more. That step-by-step, highly structured approach. Great for control, yes, but it can really stretch out development time and increase costs.
Right.
It's just hard to adapt if requirements change once you're, halfway through a phase. And in today's world, things change fast.
So you might end up building something that's already outdated.
Exactly. And trying to estimate cost overruns in that kind of rigid system, it's a real challenge.
Okay, so to tackle those issues, these different life cycle methodologies started popping up, right? Each trying to fit different project needs. The classic one is the Waterfall model.
Waterfall, the classic. It's the poster child for sequential development. One phase has to be completely done, signed off, dusted before the next one can even start. Very little going back.
And the downsides?
Well, they're pretty significant. Feedback often gets ignored because you're so far down the road by the time you get it. User involvement, usually just right at the beginning during requirements.
So they don't see anything until the end.
Pretty much. And there's this heavy focus on hitting milestones, which can lock you into early design decisions that, well, might not hold up.
I see. You mentioned a variation.
Yeah, the V model. It's basically Waterfall, but it tries to improve things by emphasizing verification and validation. You plan the testing activities in parallel with the development phases. A bit better, but still quite rigid.
Okay, so if Waterfall is strict, linear? What about the prototyping model? That sounds more flexible.
It is, much more so. It's evolutionary, iterative. You're constantly building small working versions, prototypes, and getting them in front of the customer.
For feedback.
Exactly. Get feedback, refine it, build the next version, get more feedback, repeat.
That sounds great for the customer. They see progress.
Absolutely. It's really powerful when requirements are fuzzy or changing fast. The customer sees things taking shape early on.
But the catch.
The catch is, well, you often don't know how long it's going to take, how many iterations will you need. Predicting the final cost and timeline can be really tricky. Great for adapting, less great for fixed budgets or deadlines.
Interesting trade-off. Then there's the spiral model. Our sources call it heavyweight, plan-driven, highly structured. Sounds intense.
It is, and it's typically used for really large, complex, or high-risk projects,
Right.
where failure is just not an option.
So what makes it spiral?
It cleverly combines iterative development, like prototyping, but with a very strong emphasis on risk assessment at each loop, each turn of the spiral. Plus, customer involvement is built in at each stage. You build a bit, assess the risks, get feedback, plan the next loop. It's about managing risk incrementally.
Okay. And one more traditional-ish one, rapid application development, or RAD.
Yeah, RAD. The name says it all, right? Speed and quality.
How does it achieve that?
It uses a few techniques, often intensive workshops to nail down requirements quickly, lots of early user testing on designs iteratively, and a big focus on reusing existing software components instead of building everything from scratch. It's all about getting a working product out faster.
Okay, so those models kind of set the historical stage.
Yeah.
But then things really changed. This is where, as you said, it gets really interesting, the Agile revolution.
Yeah, Agile wasn't just another methodology. It was, and is, a fundamental shift in thinking. It's a whole philosophy.
How would you define it then?
At its core, it's a process that helps teams manage projects better by breaking them down into smaller, manageable stages. But the key is constant collaboration with stakeholders, leading to steady, continuous improvement.
So, less top-down, more collaborative.
Exactly. It emphasizes self-organizing, cross-functional teams working directly with their customers or end users. The mantra is really inspect and adapt. Frequent check-ins, teamwork, accountability.
It definitely sounds like a move away from that command and control feel of some older models. Our sources boil this down into 12 core principles. The big one seems to be satisfying the customer through early and continuous delivery.
Absolutely. Delivering valuable software early and often, that's principle number one. And unlike Waterfall, Agile welcomes changing requirements even late in the game.
That's a huge difference.
Massive. It's about responding to change over following a rigid plan. It prioritizes delivering working software frequently in small increments, and it insists that the business folks, the domain experts, and the developers work together daily.
That constant communication loop.
Crucial. Plus, the human element is central. Build projects around motivated people, trust them, and, face-to-face conversation is seen as the best way to convey information.
And how do you measure success?
Working software. That's the primary measure of progress. Not reports, not how much documentation you've written. Does it work? Does it deliver value?
What else?
Promoting sustainable development, finding a pace the team can maintain indefinitely, constant attention to technical excellence and good design, simplicity, the art of maximizing the amount of work not done.
Ah, that's interesting.
Yeah, it's about focus. Trusting self-organizing teams to figure out the best architectures and designs. And, maybe most importantly, regular reflection. Teams constantly look at how they can get better and then adjust. Continuous improvement is baked in.
That's a powerful set of ideas. Flexibility, collaboration, delivering value. But it's important for our listeners to know what Agile isn't. Right. It's not magic.
Definitely not. It's not a silver bullet. It's not even really a single methodology itself. It's more like a set of values and principles that guide methodologies.
And it's not easy.
Oh, no. Implementing it well requires real cultural change, which is hard. And crucially, it's not an excuse to just wing it. You still need documentation, good design, solid engineering practices.
So no ditching discipline.
Absolutely not. And it's also not about avoiding commitment. You still commit to delivering things, but you do it in a more transparent, adaptable way.
Okay, so if Agile provides the principles, what are the actual frameworks people use? I guess the big one is Scrum.
Yeah, Scrum is probably the most popular Agile framework out there. It's designed specifically for tackling complex, adaptive problems where you don't know all the answers up front.
And it helps teams deliver high-value products iteratively.
Exactly. It's built on 3 core pillars. Transparency, making the work visible to everyone. Inspection, frequently checking progress towards a goal. And adaptation, adjusting the plan based on what you learned during inspection.
And values.
5 core values underpin it. Commitment, openness, courage, focus, and respect. They guide how the team interacts and approaches the work.
So how does it actually work? Scrum defines roles, events, and artifacts. Let's start with the roles. There's a product owner.
Right. The product owner is kind of the voice of the customer, the voice of the business. They decide what gets built. They define features, make scope versus schedule calls, worry about the ROI, prioritize the work in something called the product backlog, and ultimately they decide if the work done meets the requirements.
So they own the product's direction.
Precisely. Then you have the development team.
The people actually building it.
Yeah, usually a small team, maybe 5 to 9 people. And critically, they're cross-functional. They have all the skills needed, programming, QA, UI design, whatever it takes within the team itself.
And they're self-organizing.
That's key. They figure out how to do the work they've committed to. They deliver the product in increments.
Okay, and the third role.
The Scrum Master. This isn't a traditional manager role. They're more like a coach, a facilitator. Their job is to make sure the team understands and follows Scrum practices, and crucially, to remove any roadblocks or impediments that are slowing the team down.
Like a protector for the team's focus.
That's a great way to put it. They shield the team.
All right, roles make sense. What about the events? Scrum works in sprints.
Yes, sprints are the heartbeat of Scrum. Short, time-boxed iterations, usually 1 to 4 weeks long, where the team produces a potentially shippable increment of the product. Each sprint starts with sprint planning.
What happens there?
The whole team collaborates. They look at the prioritized product backlog and decide, okay, what can we realistically commit to delivering in this upcoming sprint? They pull work into the sprint and create a plan for how they'll get it done.
And during the sprint.
Every single day, there's the daily Scrum, a quick 15-minute stand-up meeting. It's not for problem solving, it's a synchronization point.
Oh, those 3 questions, right?
Exactly. Each person briefly answers. What did I do yesterday to help meet the sprint goal? What will I do today? And are there any impediments blocking me? Quick sync, identify blockers.
Okay, then at the end of the sprint.
2 key events. First, the sprint review. This is where the team shows what they actually built during the sprint. It's often a live demo. Stakeholders, customers, the product owner, they all attend, provide feedback, and discuss what's next. It's about inspecting the product increment.
And the second event.
The sprint retrospective. This happens right after the review, but before the next sprint planning. Here, the team reflects on the process. What went well during the sprint? What didn't go so well? What specific improvements can we make to how we work together in the next sprint?
Ah, so it's about continuous improvement of the team itself.
Exactly. It's a really powerful mechanism for learning and adapting.
Okay, roles, events. What about artifacts? You mentioned the product backlog.
Right. The product backlog is the master list. It contains everything that might be needed for the product prioritized by the product owner. Ideally, items are expressed in terms of value to the user, and the team estimates the effort involved. It's a living document. The PO is constantly refining or grooming it.
And the sprint backlog.
The sprint backlog is the subset of items from the product backlog that the development team selects for a specific sprint. Plus, it includes their plan for how they'll deliver those items. Importantly, only the development team can modify the sprint backlog during a sprint.
So the product owner can't just add things mid-sprint.
Nope. That protects the team's focus and allows them to reliably meet their sprint commitment. If something urgent comes up, it usually waits for the next sprint planning.
Got it. And tracking progress.
The most common way is using burn-down charts. These visually show the amount of work remaining over time. You might have a release burn-down for the whole project and a sprint burn-down for tracking progress within a single sprint.
Makes sense. And how are requirements often written in this world? User stories.
Yeah, user stories are a really popular and effective way to capture Agile, especially Scrum. They follow a simple template. As a type of user, I want to perform some action so that I get some benefit.
Like your example. As a student, I want to see my grades online so that I won't have to go to school.
Exactly. It frames the requirement from the user's perspective and highlights the value. And they usually come with acceptance criteria, specific conditions that must be met for the story to be considered done.
So, summing up Scrum's benefits.
Well, you break work into manageable pieces. Changing requirements don't derail everything. Team communication and visibility shoot way up. You get frequent delivery of working software, which builds trust. It generally leads to better products and happier teams when done well.
Okay, Scrum is huge, but it's not the only Agile game in town, right? What about Kanban?
Right. Kanban is another really powerful agile method. While Scrum uses fixed-length sprints, Kanban is more about continuous flow.
How does that work?
Its core principles are things like visualize the workflow, often on a Kanban board, limit work in progress, WIP. This is huge for preventing bottlenecks and keeping things moving smoothly. Manage the flow, make policies explicit so everyone knows the rules, and improve collaboratively.
So less about time boxes, more about managing flow and limiting simultaneous tasks.
Exactly. Those WIP limits are key.
And briefly, extreme programming, or XP.
XP is another influential one, very focused on the technical practices of software development. Its core values are communication, simplicity, feedback, and courage.
What are some of its key practices?
Things like pair programming, 2 developers, 1 keyboard, working together on the same code.
Really? 2 people?
Yeah, it sounds counterintuitive, but it often leads to higher quality code and fewer bugs. Also, test-driven development, TDD, writing automated tests before writing the code itself.
Wow, that flips things around.
It does, and continuous integrations, CI developers merge their code changes into a central repository very frequently, often multiple times a day, which triggers automated builds and tests. It's all about extremely short feedback loops.
Okay, that's a lot on the development side. Now, if we connect this to the bigger picture, these development methods started bumping up against how software was actually run and operated, which led to DevOps.
Precisely. DevOps isn't just a new tool or team structure. It's a cultural and operational philosophy, a major evolution. One source defined it beautifully as the union of people, process, and products to enable continuous delivery of value to your end users.
So breaking down walls.
Exactly. Breaking down the traditional silos between the people who build the software, dev, and the people who run and maintain it, ops.
Our sources talk about a shift from the old world to the new world. What does that look like?
Well, the old world often focused on, rigid upfront planning, maybe even competition between dev and ops teams, static hierarchies, measuring individual productivity, lots of assumptions.
And the new world of DevOps
focuses on delivering value continuously, deep collaboration, flexible teams, collective value creation. It embraces experimentation, learning from failures quickly, and measuring performance based on actual outcomes. Dev and ops essentially work as one team.
How does that work in practice?
It means things like setting up development, testing, and production environments to be as identical as possible, developing software in smaller chunks, and testing and deploying those chunks much more frequently, think days or hours, not months. Automation is absolutely critical here.
Right, making things repeatable and reliable.
Absolutely. The benefits are huge. Faster development cycles, delivering value to users more often, maintaining higher quality, being able to monitor application health in real time, and automating everything possible through continuous integration, CI, and continuous delivery, CD.
CI/CD. We hear those terms a lot.
They're central to DevOps. CI is about automatically building and testing code every time a change is committed. CD extends that to automatically releasing those changes to production, or at least making them ready for release. It's about speed and reliability.
And we have a real-world example from the sources, Mandrobit Solutions.
Yeah, a great case study. They built an e-commerce platform using Agile, specifically Scrum, but tightly integrated with DevOps practices using Microsoft Azure for their infrastructure.
How did that help them?
It allowed them to handle really complex, changing requirements because they were developing iteratively. Their use of CI/CD and close collaboration with the client meant they could adapt quickly.
And the result?
A highly functional platform, a really strong partnership with the client, faster time to market, and interestingly, even improved team morale. It really shows how these ideas work together in practice.
That Mandrobit example highlights something crucial. Before you can use Agile or DevOps, before you even write code, you need to know what you're building. Which brings us to software requirements engineering.
Absolutely fundamental. Get the requirements wrong, and, well, everything downstream is going to struggle no matter how good your process is.
So how do you get them right? Is there a process?
There is. Typically, it's seen as a 6-step process. First, identify your stakeholders. Who cares about this system? Who will use it? Who's paying for it?
Okay, know your audience.
Exactly. Second, establish the high-level project goals and objectives. What are we actually trying to achieve here? Third, and this is the core of it, elicit the requirements from those stakeholders. Get them talking. Understand their needs deeply.
That sounds like the tricky part.
It can be. Then, fourth, you document those requirements clearly. Fifth, you confirm them, go back to the stakeholders, make sure you understood correctly, get sign-off. And finally, sixth, you prioritize them. You usually can't build everything at once. What's most important?
Makes sense. Are there different types of requirement?
Oh, yes. The most basic distinction is between functional requirements, what the software must do, like allow users to add items to a shopping cart.
Features.
Right. But equally important are non-functional requirements, sometimes called quality attributes. These describe how well the software does its job. Things like performance, how fast is it? Security, how protected is it? Reliability, usability, maintainability.
So not just what it does, but how it does it.
Precisely. You also think about user requirements from the end user perspective and system requirements, more technical specifications derived from user needs.
What else should you gather?
You need to think about data requirements, what data is involved, how much, how accurate does it need to be, environmental requirements, where will it be used, what other systems does it interact with, and definitely usability requirements. How easy is it to learn and use?
Okay, lots to gather. How do you actually get all this information?
You use a combination of techniques. Questionnaires can be good for specific info from lots of people. Interviews, one-on-one conversations are great for exploring issues in depth, though they take time.
What else?
You can run focus groups and workshops, bringing multiple stakeholders together to discuss needs and generate ideas. Naturalistic observation is fascinating, actually, watching users do their jobs in their real environment. You learn things they might not even be able to articulate.
Like watching over their shoulder.
Kind of, yeah, but unobtrusively. And don't forget, studying documentation, looking at existing manuals, procedures, reports.
So, which technique is best?
The sources are pretty clear on this. The best approach is almost always to use a combination of these techniques. Relying on just one gives you an incomplete picture.
Triangulate the information.
Exactly. And once you've gathered everything, you need to validate and verify it. Make sure the requirements are complete, consistent, unambiguous, and actually feasible. Resolve any conflicts before you start building.
Build the right thing.
Build the right thing, right.
Okay, so we have our requirements nailed down. We've picked a development approach. Now, how do we communicate all this? Especially the design, the structure. That sounds like a job for the Unified Modeling Language, or UML.
UML is perfect for that. It's essentially a standard graphical language for modeling software systems.
Yeah.
It helps you specify, visualize, construct, and document everything from the architecture to business processes.
A common visual language.
Exactly. It reduces ambiguity and improves communication massively among everyone involved.
How is it structured? Our sources mention 3 building blocks.
That's right. First, you have things. These are the basic objects or concepts you're modeling. They can be structural things, the static parts, the nouns, like a class, an interface, a component, or they can be behavioral things, the dynamic parts, the verbs, like an interaction between objects or a state machine showing how an object changes state.
Okay, things. What's second?
Relationships. These show how the things are connected. Common ones include association, a general link, like a student attends a course, dependency, a change in one thing might affect another, generalization, inheritance, like a car is a vehicle, and realization, like a class implements an interface.
And the third block?
Diagrams. This is where it all comes together visually. Diagrams group related things and relationships to show a specific perspective of the system. And there are many different types of UML diagrams, each with a specific purpose.
Let's talk about some key ones. Use case diagrams sound important for requirements.
They are. They give that high-level overview. You see the actors, people, or systems interacting with your system and the use cases, the functions they perform. It shows who does what. You also see relationships like include for shared functionality or extends for optional behavior.
So a big picture view. What about showing how things actually interact?
For that, you use interaction diagrams. They show how objects collaborate dynamically to realize a use case. The most common type here is the sequence diagram.
Ah, I've seen those, with the vertical lines.
Exactly. Lifelines representing objects and horizontal arrows showing messages passed between them over time. They're fantastic for visualizing the step-by-step flow of a scenario, like processing an online order. You can see the exact sequence of calls.
Very clear. What's the other interaction diagram type?
Collaboration diagrams, now often called communication diagrams. They show similar information objects and messages, but focus more on the structural links between the objects rather than the precise time sequence. More like a network map of the interaction.
Okay. Now, class diagrams. These sound fundamental for object-oriented design.
They absolutely are. They show the static structure of your system, The classes, their attributes, data, their operations methods, and crucially, the relationships between classes.
We talked about relationships like association, inheritance. What about aggregation and composition?
Right, those describe part of relationships. Aggregation is a looser form, like a team has players, the players can exist outside the team. It's shown with a hollow diamond. Composition is stronger, like a house is composed of rooms. If you destroy the house, the rooms are gone too. That uses a filled diamond. These details, plus multiplicity, like 1 to many, 0 to 1, make class diagrams really informative.
So they show the blueprint of the code structure.
The static blueprint, yes. To see actual instances at runtime, you'd use an object diagram. It's like a snapshot showing specific objects and their current attribute values.
Got it. What about bigger structures? Components.
Component diagrams show how physical pieces of the software, like libraries, executables, collections of classes, fit together. They show dependencies and interfaces between these deployable units. It's more about the physical packaging.
And package diagrams.
They help manage complexity. If you have tons of classes, you group related ones into packages like folders, and the diagram shows dependencies between these packages. It simplifies the view.
Okay, moving towards the real world. Deployment diagrams.
These show the physical hardware and how the software components are deployed onto it. You see servers, devices, nodes, the network connections between them, and which software artifacts run on which nodes. It's the physical architecture map.
Very practical. 2 more. Activity diagrams. You called them fancy flowcharts?
Yeah, that's a good way to think about them. They model workflows or business processes. They show the flow of activities, decision points, branches, parallel activities, forks joins, and can use swim lanes to show who is responsible for which activity. Great for visualizing processes.
And finally, state transition diagrams, or state machines.
These focus on a single object and model its life cycle. They show all the possible states the object can be in, like idle, processing, complete, and the events or conditions that trigger transitions between those states. Really useful for understanding complex object behavior.
Wow, okay. That's a comprehensive toolkit for visualizing software. So what a journey. We started with foundations, the SDLC, moved through the evolution to more traditional models like Waterfall, then hit the Agile revolution with its principles and frameworks like Scrum, Kanban, XP.
Then we connected that to the operational side with DevOps, emphasizing that crucial link for continuous delivery.
We also dug into the absolute necessity of solid requirements engineering, figuring out the what before the how.
And finally, we explored UML as the language for actually visualizing and communicating all these complex software structures and behaviors.
Hopefully this deep dive is giving you, our listeners, a much clearer, more holistic picture of how software actually gets built. It's far from magic, but it's definitely a fascinating process.
It really is a blend of discipline, creativity, and increasingly collaboration.
So here's a final thought to maybe chew on. We've talked a lot about principles born in software: iteration, collaboration, feedback loops, visualization. How might understanding these change how you approach any complex project, even one that has nothing to do with code?
That's a great question. Could other fields benefit from becoming more agile? Thinking about prototyping ideas, getting rapid feedback, visualizing complex plans.
Something to consider. The lessons from building complex systems might be more universal than we think. Until next time on The Deep Dive, keep exploring.